the Moivre's theorem, and there it is in all its glory. Basically, we know it already, we just haven't written it like this. Because all it's saying is, when you raise a complex number to the power of n, the argument gets multiplied by n. Now that's all we've done here if you look at it. We've got cos theta plus I sine theta to the power of n. It became cos n times theta plus I sine times n theta. Now the interesting thing is the Moivre's theorem technically is just for integers n. The reality is it works for anything. So you could have negative numbers, you could have fractional powers, it still works. And we can extend the idea even more, because the other thing you'll notice is that the modulus in the Moivre's theorem is 1. But we know that when we raise a complex number to the power of n, all that happens to the modulus, it also gets raised to the power of n. So we can actually add that bit in and now cover every complex number we can raise to the power of n using the Moivre's theorem, that idea. The advantage? Well, you get something like this, 1 minus I to the power of 5. If we didn't have a theorem like this, we would have to do an expansion. Now, power of 5, I suppose that's not too bad, but imagine if the power got bigger and bigger and bigger. Imagine, I don't know, let's just pick a ridiculous number, 23. Imagine if it was 1 minus I to the 23 and you physically had to expand that out and then collect all your terms together. Very time consuming. We'll just do it with power of 5 to illustrate that. Now, if I'm going to do it using the Moivre's, I'll find the modulus of this complex number, which is the square root of 2. And the argument of this complex number is negative pi on 4. So using the Moivre's, I'm saying, well, I'm going to raise this to the power of 5. So I've got root 2 to the power of 5. I'll multiply the argument minus 5 pi on 4. Now, root 2 to the power of 5, okay, a bit of tidying up to do there. That becomes 4 root 2. The other thing you'll notice, I've changed the minus 5 pi on 4 to 3 pi on 4. We like to put things in terms of its principal argument, if it's my final answer. Now, if it's not my final answer, then it really doesn't matter which angle I use, because the cos of minus 5 pi on 4 will give me the same answer as the cos of 3 pi on 4, and the sine of minus 5 pi on 4 will give me the same answer. So it doesn't really matter whether I use the principal argument or not. But if it's my final answer, then yeah, I'll write it in terms of its principal argument. Well, if I did have to work out what that number actually is, all right, we'll go back to 1 minus I to the power of 5, which we now know is this. And then it's just a matter of working out what's the cosine of 3 pi on 4 and the sine of 3 pi on 4. We get minus 1 on root 2 plus 1 on root 2i, expand out, and we've got our answer. There it is, minus 4 plus 4i. Again, a lot quicker than physically expanding out 1 minus I to the power of 5 and collecting terms and bringing them back in. But I just said to you, it works for all powers, not just whole numbers. So we could now find the roots of complex numbers using this idea. Now, of course, we've already seen square root, and this will give us another way of finding a square root, but we can apply this to any root, cube root, fourth root, fifth root, whatever we like. Okay, because if I'm now saying that z to the power of n is some complex number, then I know I could change that complex number into mod arg form, so r cis theta. And then, to undo the power, we find the root, so we're finding the nth root of that number. So it's to the power of 1 on n, if you like. So we'll get the nth root of the modulus, and then we'll divide the argument by n. Again, it's like saying we're raising to the power of 1 on n, so I'm multiplying by 1 on n, in other words, dividing by n. But you'll notice I've done a little bit more than that. Because when you find the square root of a number, let's use that as an example, you'll get 2 answers. Well, you get plus or minus if we talk about real numbers. Cube roots, theoretically, there's actually 3 answers and forth and so on. Some might be real, some might not be. So we need to generate all the solutions, and the way we do that is, again, it's like saying, well, yeah, I had it in terms of my principal argument, but there's other numbers that will give me the same answer. And so that's basically what we're doing here. We're going around the circle 360 degrees or 2 pi each time to come up with another number that would give us the same answer. So I'm adding on multiples of 2 pi. And then when I divide it by n, I'll get different answers, and that will create all the different solutions. So I'll sub in 0, 1, 2, 3, 4, all the way up to n minus 1, because I know I need n answers. Same as the power there. Now, a little trick to this, if you know the solutions are going to be in conjugate pairs, so the coefficients were all real or something like that, then rather than going 0, 1 and so on, go like this. Start at 0 because it's such an easy number to substitute in, but then go either side, so go plus or minus 1, plus or minus 2, and so on. And that will create the conjugate straight away because you're going plus or minus. Yeah, I've said go from 0 up, but you don't have to. It just has to be consecutive numbers. You can start anywhere you like and just go consecutive numbers. 0 is just such a logical place to start, so that's why we tend to do it. Start with this one that's purely real, 4i. We want to find the square roots of 4i, and yes, we've now seen a couple of techniques, but we can now use this idea as well. Because 4i would be 4 cis pi on 2. I know z will be 2, square root of 4 is 2, cis pi on 2, but plus 2 pi k over 2. I just need two numbers, consecutive numbers, 0 and 1. That's what I'll use. Substitute that in, and I've got the two answers. 2 cis pi on 4, 2 cis 5 pi on 4. But if I want them back in the Cartesian form, then cis of pi on 4, 1 on root 2 plus 1 on root 2i, and then the other one would be negative 1 on root 2, negative 1 root 2i. We end up with those two as our answer. Root 2 plus root 2i minus root 2 minus root 2i. They're the two answers. If you think about the picture, there's another way of generating the solutions. You just find that first solution. The first solution would have been the same as if I'd substituted 0, because I would have just said pi on 2 divided by 2. Okay, that's where it is. But because we're just going around in an even amount, because adding 2 pi on and then dividing it, they will always be symmetric around. So if I've got 360 degrees, the other one must be 180 degrees away. So you get two solutions in that 360 degrees. And so bang, there's the other one, 2 cis minus 3 pi on 4. That's another way I could get the answer, because of course minus 3 pi on 4 and 5 pi on 4 would give you the same answer. Let's do a fourth root. Fourth root of 16. Now, when we were just dealing with real numbers, we would have said, oh, okay, well, that's right, it will be plus or minus whatever the fourth root of 16 is. But to pull out all four solutions, I'm going to call it 16 cis 0. And so in this case, it's 0 plus 2 pi k. Well, I didn't write the plus 0 bit down. Divided by 4. But you'll notice, because 16 is a real number, that's where I'm using the plus or minus idea. So I'll get 0 plus or minus 1, and then I'll go 2. I mean, I could have got negative 2, it doesn't matter. They've just got to be consecutive numbers. And there's my answer, 2 cis 0, 2 cis pi on 2, 2 cis negative pi on 2, and 2 cis pi, which turns out to be 2, 2i minus 2i minus 2. But again, if I did that visually, I would have said, oh, what's the fourth root of 16? 2. I know all the solutions have to fit in the circle, so therefore every 90 degrees there must be a solution. There is one. Oh, well, I know it's conjugates there. There's another one. And there's the fourth one. I get all four solutions. Find the four roots of this one. Now, they won't appear in conjugate pairs this time because we're not talking about a real number. The fourth root of 1 plus root 3i. Well, 1 plus root 3i is 2 cis pi on 3. Fourth root of 2, cis, pi on 3 plus 2 pi k on 4. Again, I won't use the plus or minus idea here because they're not going to come out in conjugates anyway. So it's, oh, well, 0, 1, 2, 3. Subbing in, there they are. But because I'm leaving my answers like this, main reason I am is cos of pi on 12. What's that? I mean, it's not one of our exact values. I mean, I could work it out using the, our cos alpha plus beta formulas and things like that. But I'll just leave it in this form. But if I am leaving it, and this is what I was saying before, if your answer is going to be left in that form, then yes, change them to the principal arguments. So my 19 pi on 12 got changed to minus 5 pi on 12, and so on. Visually, the first one would be pi on 3 over 4, which is pi on 12, so there it is, fourth root of 2, this is pi on 12. Again, so well, there's 4 of them, so I know every 90 degrees there must be a solution. So the next one would be there at 7 pi on 12, next one's there at minus 11 pi on 12, and there's my fourth one. And they all sit nicely on that circle. So they all just go around in the circle, all the solutions are there. So that's the idea of de Moivre's theorem, which is more powerful than just simply finding the power of a complex number. We can find roots as well, and that's very, very handy to be able to do that.